In this video, I'm going to explain you the atmospheric temperature, how the temperature varies with altitude in the atmosphere and different lapse rates and atmospheric stability conditions. Let's see one by one. First, we will see the atmospheric temperature. It is nothing but the temperature measured at different levels of Earth's atmosphere. It is mainly governed by the factors including solar radiation from the sun's energy and humidity of the atmosphere and altitude. It's nothing but the height. It majorly influences the temperature variations, the altitude. And the temperature varies greatly at different heights relative to the Earth's surface. This variation in temperature characterizes four layers that exist in the atmosphere. Actually, the layers are troposphere, stratosphere, mesosphere, and thermosphere. This stratification is mainly based on the temperature variation in the atmosphere. And in this figure, you can see the variation in temperature in different layers of the atmosphere. To start with, the troposphere. Troposphere is the layer just above the Earth's surface, up to around 10 kilometers and 20 kilometers, maybe 20 kilometers height. And until that height, you can see the temperature is decreasing with the altitude. It is inversely proportional to the height, and it's started to increase again in the stratopause. After the stratopause, and in the stratosphere, it started to increase again. It is directly proportional to the altitude in the stratosphere and until the stratopause. So stratopause is the simple layer in between the stratosphere and mesosphere, and after the stratopause, it is again started to decrease. So this is how it varies. The temperature varies along with the altitude of the atmosphere. And again, as the name implies, thermosphere. Thermosphere is very highly heat energy will be high heat energy will be there in the thermosphere. So obviously the temperature will start to increase and reaches the maximum value in the thermosphere. And again, the pressure, you can also look at the pressure value in the troposphere. It started to decrease in the troposphere, uh, troposphere, and it reaches very minimum value around zero in the stratosphere. And the temperature in the atmosphere decreases with the height at an average rate of 6.5 degrees Celsius per kilometer. This is the temperature decreasing rate. We call it as lapse rate. I will explain you in the coming slides. And what do you mean with the temperature range? We call it as there are variation in temperature day to day basis and even seasonal basis. And from minimum to maximum, we calculate that is the temperature range. The variation in temperature that occurs in the highs of the day and cools of the night, which means the temperature reaches the highest point, highest level in the daytime, and it reaches the minimum point at the night time. This variation is called as daily variation is called as diurnal temperature variation. And it is also based on the months or the year. As you can see, the temperature in the summer will be higher, the range will be higher, and as compared with the monsoon and winter seasons. And this variation size of the variation of ground level atmospheric temperature ranges depends on the average temperature of the atmosphere at that locality and the average humidity of the immediate atmosphere above that surface, and regimes of wind energy intensity and duration. And also the proximity to the water bodies, large water bodies, any large water bodies nearby, huge size of lakes or seas or oceans are nearby, that may also influence the temperature range. And a location which combines an average temperature of 19 degrees Celsius, 60% average humidity, and a temperature range of about 10 degrees Celsius. That means the range means the variation between minimum and maximum temperature variation. And this is considered as ideal in terms of comfort for human species to live on the earth. So the average temperature 19 degrees Celsius and humidity 60% and variation should be around 10 degrees. This is the ideal condition for human beings. And most of the places in on the earth uh, are located in the transition between temperate and tropical climates. Like in India, we are in the subtropical climatic region. So these are all the areas which are very suitable for the comfort living of the human beings. And this is for example for you, I have given this image. This is taken from the internet. The Brazil, Campinas is the city in Brazil where the temperature is measured. Here the minimum temperature, maximum temperature, and the average temperature, monthly air temperature is depicted in this figure for your better understanding of the concept. Okay. And these are all about the temperature and their variation based on the altitudes. Next, what is meant by lapse rate? As the name implies, lapse means reducing. It is decreasing rate. That is called the lapse rate. So, what are all the parameters we calculate for this lapse rate? Mainly temperature in the atmosphere, sometimes pressure also. Unless otherwise specified a particular parameter, the temperature will be taken for this lapse rate. The lapse rate is the rate at which an atmospheric variable, note this point, an atmospheric variable, any variable we can take it as. And normally temperature in the Earth's atmosphere falls with altitude. So we can take any variable, but normally temperature will be taken in the atmosphere because it is mostly influencing all the activities on the Earth's atmosphere. So we normally take temperature for this lapse rate calculations. And this lapse rate arising from the word lapse in the sense of gradual fall. Okay. And in dry air, the adiabatic lapse rate is around 9.8 degrees Celsius per kilometer. So adiabatic lapse rate, what do you mean by adiabatic lapse rate? I will explain you in the coming slides. So the value is around 5.4 degree Fahrenheit per 1000 feet. Okay, that is in the different unit conversions, and it corresponds to the vertical component of the spatial gradient of temperature. It is the vertical variation and with correspondent to the space also. And although this concept is most often applied to the Earth's troposphere, because you can expect this lapse rate to happen in only in the troposphere because there only the gravitational forces exist. So it can be extended to any gravitationally supported parcel of gas. So within a laboratory environment, within a particular container, if the parcel of gas is supported by the gravitational force, you can apply this concept, lapse rate concept. Okay, and also in the troposphere only, the temperature is decreasing with altitude. And if you go to stratosphere, there won't be that much amount of gravity exists there in the stratosphere. Also, the temperature started to increase. So if it is increasing, we can put positive signs in the formula, and if it is reducing, we can go for the negative symbol. And this is the formula: the decrease of an atmospheric variable with height, that is the altitude, the variable being temperature, unless otherwise specified. So unless otherwise specified, the lapse rate means it is only for the temperature. Okay. And typically, the lapse rate is the negative of the rate of temperature change with altitude change. So based on the altitude, the temperature varies and it is reducing. So the negative symbol comes. And the symbol tau is the lapse rate given in the units of temperature, maybe in the degree Celsius or in the degree Fahrenheit, based on the temperature value you give, and by the units of altitude. T is the temperature and Z is the altitude. So the lapse rate is equal to minus dt by dz. So next, what do you mean by convection? So convection and lapse rate, these are all the two things you have to understand first. The temperature profile of the atmosphere is a result of an interaction between thermal conduction, thermal radiation, and natural convection. So how the temperature is moving around the different particles or different gases in the atmosphere. So it is based on the thermal conduction. So some parcel of gas conducts the heat energy, internal heat energy into other particles, other parcel of gases. So that is how the temperature is conducted. And thermal radiation. So whatever the ultraviolet rays coming from the sun, it hits the earth surface. Again, it re-radiated back to the atmosphere. That is called the radiation. And the natural convection. That convection process we have to understand here. When the sunlight hits the surface of the earth and heats them up, so the sunlight heats the earth's surface, it may be land or sea, anything. Then the heat heat the air above the surface. So when the surface of earth heaten up, it again heat the air above, just above the earth's surface. When the air is hot, just above the earth's surface, the air is heating up. When the air is hot, so any material you heat them, what will happen? It tends to expand. So which lowers its density. So volume is increasing, so density is reducing. So whenever the air particle expands in volume, its density is reducing. So what will happen? The surrounding particles, parcel of gases will have higher density. This heated parcel of air will have lower density. So then it tends to rise above in the atmosphere and carry all the internal energy upward. This process is called convection. So it is very simple process. When the earth surface is heated up by the solar radiation, it heats the air above the surface, and the air becomes higher in volume and lowers the density. And when the density is lower, it tends to move upwards in the atmosphere. So that is this process is called convection. And the vertical convective motion stops. When it stops, when the parcel of gas will have lower density. Whenever the surrounding particle will have the same lower density, there the motion will stop. That is what given in this point. Vertical convective motion stops when a parcel of air at a given altitude has the same density as the other air at the same elevation. So at the point of equal density, this process stops. So that is where the convection stops. So next, what is the adiabatic process? So when a parcel of air expands, it pushes the air around it, doing thermodynamic work. Okay. So when a room or any container is tightly packed, if it is tightly packed, if some portion of air is expand means what will happen? It pushes the other particles of air surrounding the particular gas environment, and they are doing thermodynamical work. An expansion or contraction of an air parcel without any heat transfer is adiabatic process. Okay. So when the parcel of air heatens up, it expands. Okay. So there the heat transfer involves. So without any heat transfer, if an expansion or contraction taking place, means that is called the adiabatic process, right? This adiabatic process for an air has a characteristic temperature pressure curve. So it has separate temperature pressure curve. So the process determines the lapse rate. This process determines adiabatic process determines the lapse rate. And when the air contains little amount of water, very little amount, negligible amount of water, this lapse rate is known as the dry adiabatic lapse rate. Otherwise, if the water vapor is very high, and we call it as wet adiabatic lapse rate. This dry adiabatic lapse rate, the temperature decrease is about 9.8 degrees Celsius per kilometer. That is what the normal dry adiabatic lapse rate value. And the reverse occurs for a sinking parcel of air. When during the convective process, air parcel moves up, it has a low density, and when it cools down, it has the density will become higher. It contracts and density will become higher, and it comes down. That is the reverse process occurs for a sinking parcel of air. What do you mean by sinking? It comes down. Okay. And when the lapse rate is less than the adiabatic lapse rate, and the actual lapse rate is less than this adiabatic lapse rate, this atmosphere is considered as stable and convection will not occur. This convection process will not occur when the actual lapse rate is less than the adiabatic lapse rate. Okay, and the presence of water within the atmosphere, usually the troposphere, complicates the process of convection. The water vapor contains latent heat of vaporization. Okay, these are all some process which are in aligned with the adiabatic process and convection. And this image, what I have said in the previous slide, there is a temperature pressure curve for this adiabatic lab states. So the image is, this diagram is called as hemagram, showing the variation of dry adiabats and moist adiabats. And the bold lines indicates the dry adiabats, and moist line, the uh, dotted line indicates the moist adiabats lab states. Mixing ratio, pressure, and temperature are related with height in this diagram. The diagram is called as hemogram. And what do you mean by environmental lapse rate? This is like a base value from which we can compare the dry and wet adiabatic lapse rates. The environmental lapse rate is the rate of decrease of temperature with altitude in the stationary atmosphere at a given time and location. When the atmosphere is considered as stationary without any disturbances, the lapse rate is called environmental lapse rate. And for an average, the ICAO, International Civil Aviation Organization, they defines an international standard atmosphere with a temperature lapse rate of about 6.49 degrees Celsius per kilometer. So it decreases, the temperature decreases at the rate of 6.9 degrees Celsius for a kilometer altitude. Okay. Actually, the standard temperature, that means the standard atmosphere contains no moisture, which means that the environmental lapse rate is dry lapse rate. So, what are all the effects of this lapse rate on weather? The varying environmental lapse rates throughout the Earth's atmosphere are of critical importance in meteorology, particularly within the troposphere. So the meteorological variations, all the meteorological parametric variations are due to this lapse rates in the troposphere, and they are used to determine if the parcel of rising air will rise high enough for its water to condense from clouds. So this air particle rise high enough for it contains some water vapor, and they condense to form clouds. And you can also determine whether it is going further upwards in the atmosphere and form bigger shower clouds. Okay, if the density is much lower, if the temperature is very high in the troposphere, the density become very much lower and it moves further upwards to form bigger shower clouds. And again it again goes for the higher altitudes when the density is much lower, and it forms the thunder clouds. So all these things can we can predict based on the lapse rates. And atmospheric stability, it is measured based on the lapse rates. And the atmospheric stability determines whether or not air will rise and cause storms, sink and cause clear skies, or essentially do nothing. So these things determine the atmospheric stability. The stability is dependent upon the dry and saturated adiabatic lapse rates and the environmental lapse rate. So we have to compare these three lapse rates: dry lapse rate, adiabatic lapse rate, saturated adiabatic lapse rate, saturated or wet, both are same, and environmental lapse rate. So we will eventually be able to compare a measured ELR, means environmental lapse rate, with both DALR, SALR, dry adiabatic lapse rate and saturated adiabatic lapse rate, and determine the stability conditions. So there are three conditions, stability conditions. First one is absolutely stable. If the environmental lapse rate is less than the moist adiabatic lapse rate, the air is absolutely stable. So the environmental lapse rate should be less than the moist adiabatic lapse rate. When this happens, the atmosphere is considered as absolutely stable. So what will happen? The rising air will cool faster than the surrounding air and lose its buoyancy and its sinking down. This often happens in the early morning when the air is near the ground has cooled overnight, and cloud formation is stable air is unlikely to happen in this condition. And the second condition is conditionally unstable. If the environmental lapse rate is between the moist and dry adiabatic lapse rate, so it falls in between the two adiabatic lapse rates, the air is conditionally unstable. This unsaturated parcel of air does not have sufficient buoyancy to rise. So if the parcel is saturated, it is unstable and will rise. Okay, and the final condition is absolutely unstable. If the environmental lapse rate is larger than both the dry adiabatic lapse rate and saturated adiabatic lapse rate, it becomes the super adiabatic lapse rate, and the air is absolutely unstable. And the parcel of air will gain buoyancy, and as it rises below and above the lifting condensation level or convective condensation level. This often happens in the afternoon, mainly over the land masses. So the land become more heated and it heaten up the air particle above the air parcel above the land surface, and it moves upwards very easily. And these conditions, the likelihood of columnous clouds, that means that under clouds, showers, or even thunderstorm is increased because it reaches the very high altitude. And how meteorologists measure this lapse rate? They use radio sounds to measure the environmental lapse rate and compare it to the predicted adiabatic lapse rate to forecast the likelihood of air will rise and forms the clouds, and precipitation will occur. The charts of environmental lapse rate are known as the thermodynamic diagrams or hemograms, what I have shown you in a couple of slides back. Right? These are all about in this video. Thank you.